So what we know now is we know something about what is data communications. The TCP/IP protocol stack has 5 layers. You know the role of some of those layers. What we're going to do from now on, starting from this topic, is look at the mechanisms used in the individual layers, starting from the bottom and moving our way up throughout the rest of the semester. So we'll start by looking at how do we transmit data as signals across some link. I said our bit propagates from A to B across the link. How does that work? What is that bit? What is that signal being sent? First, let's introduce some terminology that we'll see. Some of it you know already. We say when we transmit data, we're transmitting between a transmitting device, a transmitter, and a receiver. Okay, so we're going to focus simply on a single link for this topic and subsequent topics. Just focus on how do we get bits from here to here. We have a transmitter, transmits a signal, the receiver receives a signal. The communication is in the form of electromagnetic waves. So we're sending some waveform. It's going to be more complex than a sine wave, but we'll see that a sine wave, the basic sinusoid, is useful in understanding how the signals are constructed. Remember, the transmission medium is the thing between the transmitter and receiver. That may be either guided or unguided. That is, the waves that we transmit may be guided along some wire or cable. So we say if I connect my laptop to the computer via some electrical or some copper wires and transmit some electricity on it, then those electrical waves are guided inside that wire or along that wire. More generally, wired communications. Optical fibres, what we do is we send light waves through some glass. It is guided inside the cable. The alternative is unguided, which is really wireless. So we can think of this as wired communications or wired media and wireless media, unguided, where we transmit our waves with no physical objects trying to guide them through the media. When I talk, we're using wireless or unguided communications. My voice is going everywhere. The media may be air, maybe water, maybe a vacuum in theory. Just the types of media or the classification of the media that we may have on a link. A link may be point-to-point or multi-point, or point-to-multi-point. Do we have pictures of these? No. Easy, point-to-point, 2 devices connected. I connect my laptop directly to the PC. My laptop sends only to that PC. There's just 2 devices, one transmitter, one receiver. The other is multi-point or point-to-multi-point, one point to many. And that's how we're communicating in this lecture. I'm talking, I'm the transmitter, there are many receivers. It's just how the communications link is configured. It may be either point-to-point or multi-point link. And the direction of communications. So this is just some terminology that we'll use throughout the course. We can have simplex communications, where the transmitter transmits and the receiver receives and nothing comes back in the other direction. The transmission or the data is communicated only in one direction. Like broadcast TV. The TV channels have some tower or some satellite and they transmit the TV signal down to your TV antenna. Your TV does not transmit back up to the tower or satellite. It's simplex communications going in one direction only. The opposite end is full duplex, where we can transmit in both directions at the same time. And in the middle we have what's called half duplex, where we can transmit in both directions but only one direction at once. The CB radios, or old walkie-talkie radios, where you press a button to talk and then you let go, and when the other person wants to talk to you, they press the button. They are built for half duplex communications. You can talk in both directions, but only one person can talk at a time. That's half duplex. Full duplex is when we can talk in both directions at the same time. So any of the links that we deal with may be either guided or unguided, point-to-point or multi-point, and one of the three directions may be used. This is the most common we see, but some systems use these. What is this lecture of the direction of communications? How would you classify this lecture? You've got a choice of three: simplex, half duplex, or full duplex. Full duplex. Unfortunately, sometimes it is. The lecture should be half duplex. We can talk both ways, but only one person is communicating at once. If I'm talking, you are not talking. But you may ask a question when I'm not talking. Full duplex is when you're talking and I'm talking, and that of course causes problems. Simplex is very boring. It's probably just me talking all the time with no questions. So it's just about the directions at which the entities can communicate. And of course we're using a multi-point configuration, one-to-many, and we're using unguided media, the air. Actually we're using a combination, in fact, because my voice goes to the microphone, then it's across guided media, and then wireless or unguided, and then eventually unguided to your ears. So that's about the links. Our transmitter sends signals, electromagnetic signals, across these links. The signals represent data. Normally we'll think in terms of bits, but we don't have to have digital data, it can be analog data. My voice is analog data, and it's being sent across this link and eventually down to your ears. We'll see that every signal that we deal with consists of one or more component signals. That is, what we do to make a signal that my laptop wants to transmit to this PC, the signal that it transmits can be visualized as being made up of many component or sub-signals. And we'll see that that's useful for analyzing and designing these signals. It's the role of engineers, communication engineers, to design the signals that will be transmitted across different links. When you buy a laptop, it has a wireless, may have a wireless LAN device. That needs to transmit signals of a particular form. Someone's designed them. And when designing them, we can look at the signals in two different perspectives, or two different domains: the time domain or frequency domain. In the time domain, if we plot the signal, we plot the strength or intensity of that signal against time. Alternatively, if we look at it in the frequency domain, we can see a plot of the peak strength, the maximum strength, or the peak signal intensity of each component versus the frequency of that component. This one will be clear. This one will explain why it's useful after we go through time domain. Here's a plot of a signal in the time domain. Here's an analog signal. We can differentiate, or we can categorize signals as analog or digital. And I think you know the difference. Analog, the signal varies in some continuous manner over time. This plot shows time on this axis, and this is the strength of the signal on this axis. The signal strength is changing continuously over time. It's an analog signal. Here, our digital signal maintains some constant level and then abruptly or immediately changes to some other level, and so on. That's what I think most people would understand if we say analog and digital. Analog continuously changing over time, digital discrete changes over time. So our signals that we transmit can be either analog or digital. And this is showing both of those signals in the time domain. Simply signal strength versus time. Another way to classify signals is a signal may be periodic or aperiodic. Periodic, it repeats. Both of these are periodic signals. They have some period after which they simply repeat over time. And this one's periodic. Here's the period of the signal. Then it repeats and repeats. Aperiodic, not shown here, but something that does not repeat over time. In our examples, or in practice, we'll deal a lot with periodic signals to build up a signal that can be transmitted. So some of the things you know about a periodic signal, if the period is this duration in seconds, then we can say the frequency of this signal is 1 divided by the period. If the period, that is, if this duration is 10 seconds, then the frequency of that is 1 divided by 10. The frequency is just the inverse of the period. This is basic high school physics. Nothing new here. So when we want to design new signals to be transmitted across some link, the way that we look at them is to look at them as a set of sine waves. So we say that the sine wave is the fundamental periodic signal that we use in communication signals. We can think every communication signal is made up of sine waves, combined in some way. Not a single sine wave necessarily, but maybe sine waves added together. We'll see them later. So here's our equation for a simple or a generic sine wave. The signal strength, S, as a function of time, is the amplitude or the peak, the maximum signal strength, the peak amplitude A, multiplied by sine, the sine function, sine of 2 pi f, where f is the signal frequency, times by the current time, t, plus phi, the phase of that signal. So this sinusoid signal is made up of, it has 3 variables there. The amplitude, the maximum signal strength, the frequency of that signal, f, pi is a constant, 2 is a constant, f, and the phase of that signal. The peak amplitude, the maximum signal strength over time. Frequency, the rate at which the signal repeats. So we saw that before. If we have some period, the frequency is the inverse of that period. The amplitude can be measured in volts, for example. The frequency is measured in hertz. 1 hertz is 1 period or 1 repetition per second. 10 hertz is 10 repetitions every second, or 10 cycles of the signal each second. We'll see some examples of them shortly. And the phase is some offset at which the signal is shifted from some starting point or some origin. So this is a mathematical representation of our sinusoid signal. And we'll use this later to create communication signals that are transmitted across links. So the basic form is the peak amplitude sine 2 pi f, the frequency, times by the current time, t, plus phi, the phase. We know that period is the inverse of the frequency. Another thing that we often use is the wavelength, lambda. Lambda is the speed of light, c, divided by the frequency. If I give you the frequency, you can work out the period or the wavelength. We only need to know one of them to work out either of the other two. To illustrate those concepts, here's a simple example of the first diagram shows a sinusoid with a peak amplitude A of 1, maybe hard to see here, a frequency of 1 and a phase of 0. So this is a plot of that. That is, the signal on the top left can be written like this. Signal 1, the one on the top left, as a function of time, because the signal strength, S, changes over time. The peak amplitude is 1. 1 times the sine of 2 pi f. In this case, the frequency is 1 times t plus our phase phi is 0. Or simplified, simply sine 2 pi t. That's the first signal, the top left one. As you change the time, here time is 0. Put in 0 here. 2 times pi times 0 is 0. Sine of 0 is 0. The strength here is at 0. If we take at time equal to 0.25, 1/4. This is 0.5, here's 0.25. If t equals 0.25, or 1/4, then if t is 1/4, then 2 times pi times 1/4 is pi on 2. 2 times pi times t, where t equals 1/4, gives us the sine of pi on 2, and the sine of pi on 2 is 1. And that's what we get at this point here. And if it's a half, then you can plug in the values of t equal to half. Sine of 2 times pi times a half, which is the sine of pi, equals 0, which is this point. This is just a plot of a sine wave where t is varying. T is time. And we could go forever if we like. It would just repeat, or this portion would repeat over time. The second signal here shows the impact of varying the amplitude. If you can't read it, the second signal, let's call S2 of t, it's the same values. Frequency is 1, phase is 0, but the amplitude is a half. That's the equation for the second signal. It's just half of this one. You see the shape is the same, except it's squished down. The height is reduced to, or the peak is reduced to 0.5 here. Instead of going up to 1, it only reaches 0.5. and repeats. The period of this signal, that is the time for one cycle, is 1 second. The cycle starts here at time 0, it finishes here at time 1. The period is 1 second. The frequency is 1 hertz. They are the inverse of each other. The amplitude, or the peak amplitude, is 1 in this case. In this case it's the same, except the peak amplitude is 0.5. By changing this value of A, the peak amplitude, we simply change the shape of that signal. Third signal, the bottom left. Our amplitude is back to 1. It goes up to 1. The phase is still 0. Our frequency is doubled. F is now 2. So we write the equation as sine 4 pi t, not 2 pi t. Here we had 2 times pi times the frequency of 1, gives us 2 pi. Now we have 2 times pi times the frequency of 2, gives us 4 pi. And if we plot this, as t varies from 0 to 1.5, then we get this shape. Each cycle takes half a second. Or in 1 second, we have 2 cycles, 2 repetitions. That is, the frequency is 2 hertz. So if we can count the number of repetitions in 1 second, that gives us the frequency of that signal. We've doubled the frequency from here to here. Amplitude, peak amplitude is the same, phase is the same, frequency is doubled. Last one, so I think they're obvious. You change the amplitude, you change the height, you change the frequency, it's more cycles per second. The last one is the phase, is this offset at the end. Amplitude is 1, frequency is 1, let's call it S4 of t. Two pi t plus pi on 4. The phase is pi on 4 in this case, here. Compare these two. This one is the same, except it's shifted along. So we take this one and we shift it back a bit. So the offset when time t equals 0, at this point the signal strength is 0. In this one it's up to 0.7 or whatever. That's because of this phase offset here, pi on 4. So the offset shifts the signal along if you visualize it. By changing these three parameters, the peak amplitude, the frequency and the phase, we can create different shaped sinusoids. And in fact, by combining multiple sinusoids together, like adding them together, in the end we can create any shaped signal. If you want to create a signal that looks like a square wave, in theory we can combine many sinusoids together to get a signal that looks like this. We'll show shortly. That is, when people design communication signals to send across links, the way that they design them is they take the sinusoid in our general form of A sine 2 pi f t plus the phase, and combine them in different ways to produce a signal shaped based on what they desire, what they think they need is good. Let's show how that works. So that looked at signals in the time domain, just as a function of time, the signal strength. The communication signals we use in practice are composed of many component sinusoid signals. at different frequencies. Here's a very simple example. S of t is our signal that we want, is made up of two sinusoids added together. Let's write it down or expand. Just as an example signal, here are two simple sinusoids with just some peak amplitude, some frequency, and in both of these cases the phase offset is 0. There's plus nothing here. What's the frequency of SA, the first one? What's the frequency of SA? Up the So you know the general form of the sinusoid, A sine 2 pi ft plus the phase. Therefore the frequency of this signal is, someone can help him? Say it louder. 100 hertz. 100 hertz, good. 2 times pi times by the frequency gives us 200 pi times t. So the frequency of this signal is 100 hertz. If you took out your calculator and a piece of paper, you could plot this. You take t equals 0, plug it in here, get the answer, and you'd plot the value. And you'd plot a sinusoid. It'll look better than mine. And over the period of 1 second, if this was 0, and somewhere along here was 1 second, there should be 100 repetitions. It's got a frequency of 100 hertz. So between 0 and 1, we should have 100 of these waves. This one, therefore, has a frequency of 300 hertz. 2 pi t. A 2 pi ft, therefore f, this is f of b, sorry. Signal b, the frequency of signal b is 300 hertz. And the amplitude here is 4 divided by pi. Here it's 4 divided by pi times 1/3. This signal here is just the sum of those two. If we add them up, we get a third communication signal. What will it look like? Well, it's not so easy to predict. If we add them together, the shape of that signal is not so easy to draw. We'll see it shortly. Let's generalize this a little bit. Instead of saying f equals 100 in this case and 300 here, we could write a general equation like this. 4 divided by pi, all multiplied by sine 2 pi ft, that's our normal format, plus 1/3 sine 2 pi 3 ft. If f is 100, then this is 2 pi times 100t, and this is 2 pi times by 300t, 3 times f. So this is just a generalization of this one, where f equals 100 in this equation. In other words, you put f equal to 100 in here and here, you'll get this. Why did we do that? Because we'll see that this equation has some pattern, and we'll use it shortly to generate a digital signal. If we have a signal of this format, so we have two frequency components here, or two signal components, component 1 and component 2. A and B are the two component signals, add them together. If the frequencies of the component signals are integer multiples of one frequency, then we call that one frequency the fundamental frequency. And the other frequencies are the harmonic frequencies. In this signal, FA equals 100, FB equals 300. This is an integer multiple of this. FB equals 3 times FA. Therefore, if we add these two together and get this, for this signal, the fundamental frequency is 100 Hertz, because each of the components are multiples of 100. 1 times 100, 3 times 100. So this is the fundamental frequency. The harmonic frequency is 300 Hertz, the multiples. We'll care especially about the fundamental frequency as we go through. Let's plot some. Here we have those two component signals in the top plots, or close to. We don't have the 4 on pi as the peak amplitude here. It's just sine 2 pi ft. You'll see the shape. And this is 1/3 sine 2 pi 3 ft. 3 times the frequency, 1/3 of the peak amplitude. You can see there are 3 repetitions when there is 1 here, and the peak amplitude of this one is 3 times of this. Here are 2 component signals. If we add them together, we get this shape. It's no longer our simple sinusoid. We can see if you add them, okay, we have a peak here, plus here we have a negative value, and therefore in the middle we get slightly lower here. So adding these two together, we get this. So by combining the sinusoids, we can get different shaped communication signals. And that's how people design the communication signals. They're much more complex than this, but this illustrates by adding them together, we can get a different shaped signal. Note that the resulting signal has the same frequency as the component signal with the fundamental frequency. This one has a period from here to here. So does the resulting signal. It repeats here's 0t, here's 1t. The resulting signal has the same period as this component signal, not as this one. The resulting signal has the same frequency as the fundamental frequency. Let's give one more example. I hope I've got it here somewhere. This is the bottom signal I showed previous slide, or on the addition of those two components. We had something like 4 over pi times sine 2 pi ft plus 1/3 sine 2 pi 3 ft. That's this one. This has two components. This one has a third component. 1, 2, 3. Here's the shape. The top one has two components. The second one has three components. The top one here has 4 components. The bottom one here has an infinite number of components. And we get our digital wave here. This is illustrating that by combining sinusoids together, we can create any signal that we like. In this case, we've created a pure digital signal just by adding together sinusoids. So if we want to design a signal of a particular shape, we can do that by combining different sine waves in different ways, and then mathematics to help us to design them to get any resulting shape that we want. What we'll do tomorrow is show how this approach relates to the data rate that we can achieve. Here we've talked about frequencies. How do we get data rates such as bits per second out of this? So that's just an introduction to that we have signals made up of sinusoids. You know that a sine is a 2 pi ft plus the phase, but we can combine them together. Tomorrow we'll continue and explain how they can be viewed in the frequency domain and how we can relate this to sending bits across a link. Let's continue tomorrow.